I want to thank StartX for hosting us. We actually went through the StartX Accelerator program, and I think we're here today partially because of the feedback and guidance that StartX gave us. Today we're gonna talk about mapping, and that's particularly mapping for autonomous cars, and how deep learning plays a part in that mapping process. So I'm going to introduce the panelists here. To my left, David Klein is a deep learning specialist and researcher. He has a number of patents and publications, and has a lot of experience in the audio and computer vision space. Next, we've got Chris Campbell, who is our mapping expert today. He currently is a manager for autonomous cars and mapping at Faraday Future. He's got a background working with Mercedes-Benz, Apple, and Here.com, and doing mapping for them. And we've also got Robert Seidel, and he is a successful entrepreneur and investor, and has experience in 3D computer vision, as well as mapping and the automotive space. So thank you guys for being our panelists today. I'm Scott. I'm an engineer at Civil Maps. I actually joined when we were focused on heavy industry, and we were making these 3D HD maps for heavy industry, the railroad industry, road, as well as utilities. And thanks to also StartX, they introduced us to a lot of automotive companies, and we got this pull to go more towards the autonomous car market. So that's another thanks to StartX. So we'll get started with some questions, and we're gonna talk about mapping and how that relates to autonomous cars. So for our panelists here, how do you guys see mapping fitting into the autonomous car ecosystem?
Do you want to throw it to somebody, or what's the procedure?
I don't know. I think we're just kind of figuring it out. We can do Chris.
Yeah, well, I see the map as being, especially at first, being an integral part of autonomous driving. Kind of see it as a sort of a backbone of the process where you have you have a map as a backbone of the system, and then as you drive with sensors, the sensors can refer to the map and understand what the differences are. It extends the range of the sensors. Horizon. You have a horizon. The map gives you a horizon of the.
I'll turn you up.
There we go.
Yeah.
So the map is there as sort of a reference, and I think the map and the sensors working together is what initially will be what drives the autonomous car. And again, you need an engine to ingest the map and the data and the sensors to work together.
Okay. Robert.
Yeah. First of all, thanks to StartX. This is a great space. Last time we were here, Mark Fields was here.
Oh yeah.
And you guys were here too.
Yeah.
So just in the interest of full disclosure, we are investors in Civil Maps as well as Quantity that does LiDAR sensor. So we are very bullish on this space. Maps for autonomous driving and for ADAS, for advanced driver assistance systems, are very different than the maps we're used to today on Google Maps or Apple Maps or Nokia Maps. Those are made for humans, and routing is for humans, and instructions are for humans. The maps that we need for self-driving and for driver assistance systems are many orders of magnitude more precise, more dense, and they need to be updated more often. And so the traditional work pipelines that we have for making human maps don't fit that model very well, because we need to process gobs and gobs more data much more often than we are used to today. That's number one. Number two, all the people that are creating self-driving cars or ADAS systems for such cars are actually putting sensors in cars that can help make those maps. which is a very different business model than what we've seen before, where you had map companies collect map data with very expensive $250,000, $1 million cars. That business relationship about who collects the data and who gets paid for it is also in transition. And both those facts, the technical transition and the business transition, create an opportunity for new companies where otherwise there might not be much opportunity if there were just entrenched players. So that's why we're bullish on that space, and new players and smart people like yourself.
That's great. Could you go a little bit more in depth between what differentiates a human map, like a Google map that you navigate, and an autonomous vehicle map?
Sure. So for example, a human might need to know to go from here to California Street, you turn left at the exit, and then you turn left again at the red light, and then left at El Camino, and then you go right. If you're an autonomous car, you need to know every 10 centimeters that you're driving where you are. So echolocation, where you are in the world, is a really important, with respect to the rest of the world, is an important problem to know. And if you don't want to go over sidewalks, or you don't want to go into potholes, you need to know that data with high precision and high accuracy, high granularity. The other thing that's important is sometimes a particular sensor, like a radar or a LiDAR or camera, won't see things because the Earth might be covered, not here in California. Well, actually, if you go up 80 in the winter, in good years, you can actually see snow. And then everything is covered with snow, so you won't see things on the road like lane markings or berms or things on the side. So how does the car know exactly where it is relative to everybody else? So it's important to not just have a 2D map, which is what all our current geo systems are, but we need 3D. We need things sticking out of the, just like when you go up 80, you have these poles, and it's snowed in 3 feet, you can still see where the poles are, and you try to stay between those poles. Well, self-driving cars need the equivalent of that all the time.
All right, so we're trying to create these detailed maps so that autonomous vehicles can travel around. What is involved in creating one of these maps? Yeah, get that right up there.
So traditionally, you have maps from, like I'm talking here, created with GPS, which is 3 to 5 meter accurate. So today we need sub 10 centimeter accuracy, and so the GPS technology doesn't really work for that. So what we need is mobile data collected via LiDAR or other sensors, as well as some survey techniques that can create the map quickly or collect the data and scale over large areas. So I think it's a difficult problem, and right now there isn't really a map available, and I think that's one of the biggest slowdowns for the autonomous car is the map is really not there yet. Data needs to be collected, it needs to be processed, and a map needs to be created that's accurate enough to sit in.
Can you go into a little bit what does processed mean in this context?
Data, a lot of what the data is collected first, and then you have processing, which would extract features, stuff like lane, how wide the lane is, how many is the lane, is it a solid white line, is it a solid yellow line? You need to know pretty much everything that's on the road. You need barricades, you need barriers, street signs, everything that you would see as a driver. That needs to be collected, processed, and then created into a map. And the map that we're talking about is not like a visual map you'll see. It's something that resides on the car, and the car can use its sensors to compare to the map. So the map is not something that we're used to. It's not like a Google map or a street map that we normally see. There are technologies that you can use to display that, like on a HUD, but the map itself is purely for the car to compare.
Okay, so how specifically would you go from, I've collected all this LiDAR data, Now I want to go to, okay, here's where a stop sign is. What is the current process, and what is the industry standard for going from here's all this LiDAR data to here is the outline of a stop sign?
I don't know. So I'm working with Faraday, where we're kind of looking at different areas of identifying features from LiDAR data and then setting up ways to process that. Faraday is not really in the business of mapping, but we will work with partners to kind of define, give you requirements, specifications, that what we're looking for in terms of what we need from the car. Large area, I mean, it's easy to collect a lot of data. The problem is extracting features from that data and putting it into a car that can read that. Some of the details are kind of protected, I guess, but you know, like there's a couple ways to do it. You can do aerial LiDAR, you can do different imaging, survey information that you can collect, and then create a map. The map is lane level specific, so it's instead of a line, you have multiple lines. You have each lane has their own semantic information. You have this lane has a specific signal that's attached to that lane. In this lane, you have to turn left and go straight. So each feature has its own representation. And as you create the map, you have to tell, these features are being extracted, and you have to give meaning to what you're extracting and then put it into a map.
When you're saying extracted, is this like someone labeling it, or is it a machine learning algorithm? What does that look like?
Ultimately, you'd like to process it automatically, but traditionally you can get less than 50% accurate, pulling that stuff out. And then you get a certain accuracy with that. And then if you have to make adjustments manually, you introduce a number of errors. And so you can't really get it consistent under a requirement of, like, let's say 10 centimeters. If you introduce manual processing to the features, you introduce manual error. So you could have 10 centimeters in certain areas, but then it could jump to 100 or 200. So you have a bunch of holes in the map. So the difficult part is teaching your computer to understand what the features are. So if you can get that 50% to like 75 or higher, that would reduce a lot of the workload.
Okay. Just to fix definitions, the accuracy you're referring to, is that the semantic information or is that location?
That's location.
So placement within some boundary within a margin, you're saying?
Yeah.
Okay. So you're trying to extract all these different features, and there's a manual process associated with it that can lead to additional error. I think here's where we've got some expertise from David, has a background in deep learning. David, what are some sort of similar problems that you've seen, and how have you seen deep learning applied to them?
So deep learning has enabled large strides in object recognition in images. I think a lot of us are familiar with that at this point. Also, large strides in audio recognition, in particular speech recognition. And what you'll see in a lot of the headlines is, okay, here's an image, tell me what's in it, or tell me the top 5 objects that's in it. That's sort of like the headline. That kind of capability has undergone a step function in performance. These new advanced deep learning-based machine learning methods have come along in the last few years. More generally, if you look at an image, there's a few different things you want to do with it. Number one is recognize objects in the image. Number 2, you can recognize attributes of those objects. 3, you can place bounding boxes around those objects. And then 4, you can actually segment those things out at a pixel level. more recently, in the last 2 or 3 years, and this, a lot of this research is based on research that's gone on since the 80s, and we can talk more about what's enabling these step functions now. But we also have now the ability to do this kind of segmentation and recognition on not just 2D images, but 3D volumes, or 2.5D, RGB and distance.
Could you go into a little bit what is 2.5D?
So the input to these segmenters and recognizers usually have as an input a stack of feature maps. So if it's just a grayscale 2D image, you just have X, Y pixels, horizontal, vertical pixels. If you have a color image, you have a stack of 3 color planes, red, green, blue. But the methods that are being used now are very extensible. So you can actually input as input a number of other feature maps. And sometimes they're just kind of hand designed still. So for example, if you're looking at motion, you can have another map that's at the same pixel level, but it's just telling you something about motion direction per pixel.
I think we've got some.
Hello. So 2.5D specifically refers to that last feature plane going into these segmenters and recognizers corresponding to a distance measurement.
Okay. So you mentioned hand-coded features. What are hand-coded features? What are the pros and cons of having hand-coded features as part of your learning algorithm?
So mostly cons, as it turns out. It turns out that, yeah, and I think if we think about it a little bit, you probably can believe that, a single person building up, let's say an academic life worth of understanding of a problem, and yes, again, it's built on other people's work, but, we come up with some conceptual understanding of a problem, and we say, okay, this is an image, this is a face, I want to recognize faces. I know that a face is composed of eyes and a nose and a mouth, and the relationship between those things says something about somebody's identity. So I'm going to, okay, now let's talk about the eye. An eye is composed of, an iris, and it has these patterns. And I'm going to program. I'm going to sit down and program a way to say, okay, if I detect edges, that go and have a circular boundary of this size, that has, that's an eye, and et cetera. With deep learning, one way to understand deep learning is that we're starting from rawer and rawer data, like just images going in, nothing about hard-coded features, hand-coded features. We're just going to throw a lot of data at this algorithm, and we have ways of now breaking up the problem, carte blanche, to a neural network that has many layers, potentially more than 100 layers that are executed in sequence. And it's a hierarchical feature learning problem where we go from very low-level features that are important for parsing, for example, the edges of an image, up to higher-level corners, now to contours, things akin to eyes. We can introspect these networks and see what they're doing, but we're not really placing any constraints. And so we find that by throwing many millions of examples in some cases, sometimes hundreds of millions, that we can use these very deep networks to learn what the appropriate sequence of processing steps are. And they far outperform what we've learned to do as puny little humans with our lifetime of experience.
Okay, so bringing it kind of back to this mapping and creating these detailed maps for autonomous cars. Chris, how many assets do you think you would say if we wanted to map all of the US, how many different types of assets do you think we would have to label? It could be a rough estimate. Can you get the mic up?
I don't know.
Maybe also, you say a word asset. I don't know whether anybody, you know,
Asset,
assets,
yeah.
a lot of people have assets in Wall Street. So
Yeah.
I think what you mean is
Yeah.
classes of things that might be relevant to recognize. So
Yes.
light poles or fire hydrants or traffic lights, stop signs. I mean, is that what you mean?
It's exactly what I mean. Thanks, Robert.
I'm not exactly sure. I mean, definitely streetlights, anything that's on the road that would affect navigation, crosswalk, curbs, but you also have to understand what the color of the curb is, you know. So, you know, there's a lot that goes on with the different assets.
Okay. How many street signs, different types of street signs, do you think there are in the U.S.? Maybe that's a better question.
I think if you count the different street signs and the different kinds of lane markings, you're in the hundreds.
You're in the hundreds.
Yeah.
So potentially kind of going back to what David was talking about, you have a hand-coded feature approach where you're going around and saying, okay, a stop sign has this angle around the edge. Okay, we found that. That's a stop sign. Let's move on to the next type of sign. So now you're having an engineer write a specific algorithm for each type of sign.
Yeah, that's right, yeah. And that's one of the shifts we're seeing, and is that we're seeing a shift from people with expertise in image processing that can code these things up to more upfront data collection and also greater investment into compute resources. And maybe you have questions later about that, but what we're seeing right now as one of the bottlenecks is in this new process is the collection and annotation of data.
Could you go into that a little bit more?
Also, I've worked with and in a large number of companies over the last dozen years. I've been out here in the Valley, and I've learned, you know, as I engage with a company, to basically ask about the data on the first step, because one of the advantages of hand coding features, you know, humans are not total dullards. I mean, we do have some good ideas about what are reasonable features, and by putting those in a system, you are alleviating some need for this deep neural network to learn those features. That means that you potentially need less data to get to a certain level of accuracy. But then you have a ceiling on the accuracy. When you go carte blanche from data, no expectations, you have to have enough data. And for complex image recognition tasks, the amount of data tends to be in the, let's say, hundreds of thousands of examples at least, to get to very high levels of accuracy that you care about in these mission critical products. And so, you know, there's now a bunch of different mechanisms popping up to do that. You know, some people get clever and they hire teams of people through Craigslist. You know, now there's organizations like Crowdflower that specialize in data collection. If you happen to have an application where you're in a data stream and you have the ability to do some sort of labeling as a part of what the product is, that's the best situation ever.
Okay.
Because you can run into the problem if you crowdsource, you have a certain level of accuracy, as what you brought in before, and humans will make errors, and certainly not highly trained humans, like the ones that you get on Amazon, Mechanical Turk or Crowdflower, and that kind of upper bounds the accuracy that your system can have if you garbage in, garbage out it.
Okay, so you're saying that we have, so if it's manually annotated, these different sorts of, I call them assets, but they're different objects on the street. If we already, so we have a ceiling right now because we have human error as part of that process of labeling it. What sort of methods have you seen in machine learning to sort of skirt around that bottleneck of like having to rely on humans who could be inaccurate annotating and labeling your training data?
So it's actually a big problem right now. I mean, it's now that we're seeing these systems and you know, become the new way of doing things. You know, it's one of the big issues, and I'm not going to claim that it's solved. But more and more of these systems recognize this, that, as you're engineering systems into your company, so it's not about some upfront data collection of your, diamond-plated data set, and then, a month of training and then you're done. It's more an iterative process. And so having experts in the loop where you can sample from the system and correct errors and incrementally make improvements is as far as I've seen, kind of the state of the art.
I think also that the deep learning algorithms, well, maybe we should push back a little bit because we talk about training and just to talk about how these deep learning systems actually learn is you have to provide them with raw input data, whether that's just pixels or a voice stream or a bunch of LiDAR points, and you have to tell them what you see. It's like a baby. You say, daddy, 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 100 times from different points of view, and eventually the baby will figure out, okay, that face is daddy and that is mommy. And so those are called training samples. And that when we talk about labeling is basically a human going through and saying, that is a dog, that is a shepherd, German shepherd, or that is a terrier. And so these are labeled data sets then. And to get these labeled data sets is fairly labor intensive. And so people like at Google have taken, for example, huge data sets that are publicly available, like Flickr, that are, or Yahoo, that are tagged with certain things. So they're geotagged saying this is the Eiffel Tower or this is a beach ball or something like that. And so they're kind of tagged. They're not very accurately tagged, but they're kind of tagged. And so that's one shortcut to that. Other people have taken multiple sensors and tried to create a training set with one set of sensors to create the learning machine for the other sensors to make it less abstract. If you have a LiDAR that can detect street signs just by, these are highly reflective things that are at 90 degrees to me, that are on a stick, and that are about this size. And that filter is often enough to say, okay, that's a street sign. And then you cut that out in the video image that's corresponding to that LiDAR image. You basically say, that's a street sign, that's a street sign, that's a street sign. And later on, you can give random video signals to the learning network, and it'll say, oh, there's a street sign. So you can use multiple sensor modalities to make your training set. But one of the problems is, like you said, you can't just train it once and be done, partly because if you use the same training data over and over again, you can overtrain, and you'll exactly recognize what you told it, that picture of daddy, that picture of mom, but not the other things that you're supposed to recognize. And there's a whole science behind overtraining and that's worth it. The problem in our world, what we're making maps with cars, is that we have not just the training example here, but the training example in Germany, and then in Italy, and then in China, and in Korea, where the street signs are different, the road markings are different, the cars are different. So it's not just a one-time training problem. It's a huge continuing training problem that's geo-specific, actually.
Okay, so how would you potentially get around the problem of having data that looks different in different geographic regions? How can you try to get that training data in some sort of scalable fashion?
Well, people have done, I don't want to monopolize it, but I'll just say that you can simulate. So what people have done is they've, Conti, for example, where it's pedestrian detector, they've taken video, and they've driven around, and they have, 60 hours or 80 hours, and they take that video, and then they don't just present the basic video, but they stretch it, and they rotate it, and they do all kinds of affine transformation. The thing still has to recognize that that is a pedestrian. That doesn't scale all the way, because you really don't have full three-dimensional recognizability. But we have great computer graphics nowadays, and you can actually simulate humans, or when you look at the latest movies, there are all kinds of computer graphics that look totally realistic. So can you present the computer graphics from any angle to these systems and basically create training sets that are already labeled? Because you know that that's a person, because that's your database says before you render it, so it's pre-labeled.
I agree with that. Yeah, there's sort of these at the forefront now. These production systems we see simulation, which is what you're talking about. You talked about all three things: simulation, augmentation is introducing warpings and noise and all kinds of stuff into the data set to make the system expect the unexpected. And then we have normalization. That's another important aspect of it, where you know, for example, with face recognition, we can recognize faces no matter, you know, how the face is rotated, as long as, you know, you have a profile visible. And there's some face recognition systems that do upfront normalization, where you actually have a 3D model, a mesh model of a face, and you sort of rotate in software. If you get a side view of a face, you can partially rotate it to a frontal view. That eliminates some variance in the data. So if you have some normalization specific to signs, you can be more robust to the variations that are out there. You know, most of the larger companies will say it's all about data. You know, you're going to get the best performance by getting more and more data. Augmentation is nice and normalization is nice, but we're going to end up blowing past all those tricks with more data. Part of it is that they have in their own interest to say that, because they're the only ones that have this data. And so I guess one more thing I'll say.
Don't try to compete with that.
Yes, yeah, that's a big part of it. But one more thing I will say about that is that there is a natural countertrend that is starting. It's sort of baking in the normalization into these networks, so they have more and more specialized architectures that deal with the kind of variances that objects have in the real world. And so with smaller architectures and less data, we're going to be able to see the same kind of performance. And so I don't know how far and when exactly that pendulum will swing, but I'd be aware of that going into this, thinking that, okay, my 5-year play is to collect the biggest data set that's out there and that I'm going to be winning. I don't think that's going to be the play in 5 years.
So what were those three that you mentioned again? It was what were those? Transformation,
augmentation, normalization, and simulation.
Simulation. Okay. How would you apply those into like a LiDAR point cloud application? Too tough a question.
Well, okay.
Stumped you guys.
Well, on the LiDAR side, driving simulators have been around for a long time, and they have been originally used for putting humans in a simulated car with a screen in front of you, and then you drive around and you see how well the human reacts to the driving tasks at hand. Well, those visual simulators are now also being used to simulate what the sensors would see in the car. So, for example, imagine you have a camera in the front of your car. Well, that camera has a certain field of view and has a certain color range that it can see. And so you can basically take that segment of what the simulator creates and say that's what the camera would see. And then you can simulate things like the distortion that the lens would create. Like, you know, a cheap camera has a very strong, or a wide-angle camera has a very strong distortion. And then you might have drops of water on that camera or dust that in the real world you would have also. And all those things are simulated, and the end result of that is then given to the sensor system that simulates what the rest of the system should perceive. Because a drop of water could, you know, enlarge a car that's very far in the distance to look like it was very close. And the system has to be able to detect whether that's an erroneous proximity or is basically a correct measurement. And so you can do the same thing with LiDAR sensors, where you, instead of getting a camera image from the simulator, you shoot beams. This is called ray tracing. A technique's been around since the early 80s. You shoot beams from each pixel into the scene. You say, what do you hit first? And that's basically the same that a LiDAR would see. And you do that many millions of times a second, and you can see all the points. And each point would give you a distance value and the reflectance value. So you can, in the computer, generate what a real laser scanner would see. And that takes a lot of processing, but the tools now exist to do that. And the Germans, in fact, have been, you know, avid users of the German OEMs, have been primary and early users of those techniques.
Okay, so now we can, maybe it's not exactly like the real world, but we can create some training set that we know is at least 100% accurate for that simulator because we created it.
That's right. But I don't think it's going to be as messy as the real world is. Whenever you go out into the real world, it's amazing how many special cases and how many rules get broken. And so there's a lot of stuff beyond the basic training, but at least you have that labeled data set to begin with out of a simulator. I think that's very useful to begin with.
So where I've seen similar things applied, not with LiDAR based point clouds, but 3D mesh simulation, and yeah, so it's for robotics, for example, robotic navigation based on computer vision, and even in that case, you can't take the simulated learnings and transfer it to the real world without additional work, but it does give you a big head start. So you need a lot less data. And there's different schemes of doing that. There's some specialized architectures, again, to kind of adapt what you've learned in simulation to the real world. As you can imagine, there's some tricky things in there, having parallel, in some cases you want to have like parallel simulated and real world experiences so you can learn that transfer function. Other times you can just kind of take a pre-trained network and have that as your starting point and learn from that starting point with less data.
Okay.
I'm not paid by NVIDIA, but I will give them a plug because at the conference they have every year in San Jose, I think it's in March or April, April 4th. Last year was all about neural nets and how to use them for self-driving problems, and both the keynotes by Jensen and the more detailed presentations afterwards really explain well both the history of neural nets and the tremendous amount of development and innovation that's happening there at the moment. And I highly recommend you can just Google for NVIDIA GTC on demand, and you can see all the videos there, and a great introduction to that field without requiring a PhD. And going from both the algorithms to the actual application in detecting cars, for example.
Cool. That's great. I want to try. I think we've gotten pretty deep technically. Want to try to get a little bit more big picture. So we're creating these maps, these detailed maps for autonomous cars. How do those maps relate to what the car is seeing real time, and what's sort of that handoff? You have a map that's already there that's saying, okay, here's all the lanes, here's all the stop signs. How do you take that and work with something that's real time, looking at everything?
Well, you have the sensors, and then you have sensor fusion in the car that can understand that, and then it communicates internally to reflect what's in the map. So you have the sensors basically working in conjunction with the map.
I think you got to get the mic up there. Yeah.
Basically referring to each other. The sensors say that this is here. The map says agrees with it or not. And then if you have a discrepancy, the car can save that data for an update later. And vice versa. If something's in the map, not seen by the sensors, if something in the sensors, and then as it goes, it can learn what these things are. The map is, at first, it's going to be there just as a reference. Keeping the sensors honest, saying, okay, sensors are seeing this, is it reflected in the map? I think over time, the map doesn't have to be as accurate as you collect more and more data. You'll be able to create a map in real time, basically. In 10 or 15 years, I think the accuracy of the map can go down, but at first, you need a very accurate map. And then as you develop more and more data, you build your own self-sustaining map.
Okay. What are the trade-offs between having a more accurate map and a less accurate map?
I think in terms of horizon, the vehicle can go a lot faster. You know what to expect, what's coming up. You've seen a lot of examples of where things don't exactly work correctly when you rely only on sensors. There was a cruise automation where the handoff between autonomous and driver didn't happen so smoothly. So, the sensor detected something and started to drift, told the driver to take over, and the driver needs about 10 seconds to orient themselves to what they're doing, and the driver overcorrected and then crashed into a parked car. So I think the handoff is, sensors are going to say one thing, and if you don't have the map, you don't have anything else to refer to. So the system they were using was sensor only, and the sensor failed, and there was nothing to reference. And at that time, the car just gave up and said, okay, I can't do this, you take over. And it didn't give the driver enough time to react. A lot of car companies are safety conscious, and they don't allow that to happen. Mercedes has a self-driving car, but there's a certain route clearance that will be given to the driver.
Route clearance is just where you can drive.
Where you can drive.
Okay. Because they've mapped that
Yeah.
in detail.
Right. Or they don't. Yeah, they're not. They're very safety conscious, and they have to have backup systems. So you have to have a sensor and a map to understand it. And if those don't match, it says you have to drive. We can't handle that situation.
I want to perhaps elaborate on, you asked the question about precision, and you actually brought up the example of human. So there are multiple levels of automation, which I'm sure everybody here is familiar with, but the ADAS, the driver assistance systems, where you have either sometimes automation or often automation, is different from the full automation where the driver is basically taking a nap. And we already have maps for the level 2, level 3 automation where the driver is still...
What are the levels?
Okay, so I'm going to keep it very brief. Level 1 is, you drive. Level 2 is sometimes computer drives for you. Level 3 is often the computer drives for you, and level 4 is always the computer drives for you.
Perfect.
I'm not doing it justice, but that's kind of it. So we have for level 2 and 3 systems, level 3 systems are just coming out now, but we have maps for those out there, and they're called Electronic Horizon or E-Horizon. You may have heard about ADASIS, things like that. And they're treated as an extended range sensor. So your radar has a certain range, your LiDAR or your ultrasound has a range. Well, a map has a range that goes beyond visual range, beyond direct line of sight. And so that's useful when you're on the Autobahn, you're driving 170, and there's a sharp curve coming up. It's useful to slow down before that sharp curve comes, because otherwise you're going to take a bath, or you have to brake really hard. And so it helps the driver assistance systems to look ahead. And that can also be, the driver assistance systems may know there's an exit coming up, so slow down because people are going out or in. There is a wet condition coming up that's usually icy when it's cold, so slow down there. So these are extended range maps. They're far lower precision than what we're talking about with the LiDAR, but they're already electronic assistance maps today for level 2 and 3 systems. For level 4, when the car basically has to drive itself all the time, reliably, you need these much higher precision maps, because one of the tasks is to echolocate, to figure out where the car is with respect to the road. And that's a centimeter kind of accuracy problem. And again,
why is that important?
Well, because otherwise you might, let's say you want to go across an intersection. Well, if you don't know exactly where you are, you might be shifted slightly. In the computer's mind, you're shifted slightly. Well, you're going to drive right into that berm that's dividing the lanes or has a big pole in it. Or you do quick obstacle detection just before, but the car is not going to drive like a human it would. It's going to drive very erratically if you don't have that information. It's always going to be in conjunction with sensors that adapt at the last minute for obstacles and the actual real-world situation. Because even if the map says, the map will have errors, always, just like the real world has errors. So if the lane markings are like this, but somebody has put cones out because there's an accident or construction site, the map will say just go straight. And the other systems, including the sensors, will say there's an obstacle here. And the derived sensors, such as the paths that other cars take that you measure, that the car in front of you, that's a useful signal. That's a useful sensor to have. Where's the car in front of me going? Because it's probably better to follow him rather than to go into the cones. And so it's another sensor, and you always have to fuse all these signals to arrive at a conclusion. But for completely self-driving cars, you need much higher precision maps. I mean, centimeter accurate maps.
Mm-hmm. Okay. So we're talking about redundancy and how different data sources increase your confidence and then increase your operating envelope. Okay. Jason, how are we doing on time right now? Okay, cool. So I guess kind of big picture, what are some of your big takeaways from this panel? If the audience left with, yeah, if the audience left with kind of one takeaway, what would you say that's maybe non-obvious coming in?
All right, I'll jump in. We've talked about this just before we came in. One of the things that concerns me, or I don't have an answer for yet, is that the speed at which these neural networks gather knowledge and gather understanding of the real world is so much faster than human programmers that it is going to be increasingly hard for CEOs to say, we're going to keep the human programmers and the strict algorithms that we code review and all these systems that we have in place for engineering standards. I mean, these networks are just too good. We should use those. And the problem is in the car industry, I mean, it's different when you recognize a face on Facebook. Oh, you were at that party yesterday. I saw you on Facebook. Facebook told me, you recognized you. But if you have, that's okay, you make an error there, you could, get into problems, but it's not life-threatening. If you are driving at 60 miles an hour and the thing says, oh, I think that's a person, I'm going to evade it, and you go and crash into the side just because the car thought it was a problem, and it just turned out to be a paper bag that was blown by the wind across the street, that's a real problem. And so how do you validate the correctness of these systems? And to date, the car industry has been extremely conservative, with reason, to introduce systems that that can be introspective, where you can say, well, you wrote that if statement that says, if I can't go straight ahead, then first try right and then go left. Well, it turns out that you drove over the grandmother on the right-hand side first. Well, then somebody can look at that code and say, well, you did that, or that code was responsible. With a giant set of weights, you don't have the ability to go in and see what was actually the cause of that. So there's a whole set of academic research, I think, that still is to be explored. If we're going to accept these systems because they're so damn good, and they're getting so damn good so much faster than humans, how do we test for completeness, correctness? How do we make sure that if we do find a problem, that paper bag, okay, fix that particular bug? Because in code, that's one extra if statement, so making it simple. But when you have a billion weights, how do you fix that? So that's just a question. It's an open question mark for me, how to do that.
I think in terms of the map, it's difficult to collect the data. It's difficult to extract. It's difficult to to create the map itself, and it's difficult to get the map in the vehicle. So there's a bunch of problems that are still yet to be worked out. There are quite a few companies working on these problems, but we're still a long way from having a map that's accurate enough for autonomous driving.
Yeah, I think to that point, I'm actually curious to hear real numbers. If we wanted to have, a majority fleet of level 4 cars, how much map data would we have to collect out in the world? There's one thing having, Google cars going around the Bay Area, Mountain View, but how many miles of roads are there out there, all the variations in all the countries, and there's just going to be absolutely no way that we can do that without deep learning or whatever its successor will be. We have to have means of processing that data, labeling it, verifying it with computer vision and with systems that have yet to be developed that are specific for this kind of data set and these set of tasks. And so it's a really exciting time right now to be getting into this.
Maybe from a business perspective, one of the changes is that you don't have individual makers of maps like we have today that drive their fleets of 50, 100, maybe 1,000 mapping cars around. In future, every car will be a mapping car, or some subset of the fleet. But today, we have 50,000 Model S's, and some significant subset of those have the cameras in them, and they're already mapping. So that's already bigger than any mapping fleet today. Okay, most of them are in the Bay Area, but anyway.
I actually saw one on the way here.
Yeah, but so that changes the dynamics of the business when the car makers are actually the originators of that data. Each car maker doesn't want to become a map maker. So that begs for independent third parties to become aggregators of that data. And maybe in the beginning it'll be specific companies. In future I could see that there's a market for the data, like an open market. You upfeed and the data is valued, and maybe certain cars and certain sensors are valued more than other cars, or particular areas are valued more where you don't have enough coverage yet. So that creates new business opportunities that I don't think are there today.
That's great. I'd like to open it up to the audience to try to get some interaction here.
Absolutely. So we're going to take questions with this microphone. 2 people have come expressing interest in asking questions, and the first one will come right from here. There you go.
Hello. So I have a question. Like, when you train all the train the machine or the algorithm actually to understand those labels, you can either go with different images and try just like what you said, you box different roadside and try to give label of it. But my question is it going to be a better suggestions? Like I just have it in my mind. Like, let's say you have a video that you stream it to the algorithm. It's a video that they take it from a car. People just drive it around, and by that. They don't care about if there's a stop sign or red light, but in another sense, we try to train the machine that when they see those objects, they stop the car instead of trying to identify what they are, because it doesn't matter what they are, what the machine thinks they are. Most importantly, it's like they just stop the car, right? So if you have a video that actually input to the algorithm, then it can either maybe more specific just to focus on specific patch of area to look at if there's a red light or a stop sign. So that's my question. Is it going to be a better way of training instead of just inputting a whole bunch of stop signs or road signs?
So are you saying using additional data sources, like the car's
All I'm
movement?
thinking is like using video instead of using a whole bunch of road sign image to train it. So, well, it kind of trained it with a driver's perspective of, oh, maybe at this area that I should expect some sort of sign. Right? Then if it's red or whatever the algorithm trained it to be, then I just stop the car. I don't have to care if it's a red light or stop sign. Yeah.
I think that's pretty insightful. I think that, that there will be ways of moving forward in that direction where we'll have a scene understanding of, a point cloud or images without necessarily having to segment out the stop sign itself. I mean, at the very least, it can be a way to accelerate the creation of data sets. You can have this kind of staged approach where you're able to sort things in terms of scene understanding. So if you want to account for a certain scenario, let's first sort things into a scene understanding of, okay, this is coming to a stop at this sort of intersection, and that is comprised of various parts and as a whole. So I think that's a pretty interesting idea. The other thing I would say, just on an adjacent topic, there is something we haven't talked about called unsupervised learning, which is a exciting area of research right now. It's one of these holy grail areas that again harkens to the way people actually operate. As we're going through the world, we see something, we recognize it as being novel. We see multiple examples of this in different scenarios. We're able to understand this is a thing. This is the kind of sign that I haven't seen before, and there it is again. And you can collect a bucket of those things and then present it to your parent and ask, well, what is this and what does it mean? that's very different from, having to go through individual time slices of LiDAR data and identify assets. So that's going to impact things as well as that comes into fruition over the next few years, hopefully.
A question here on the right.
So my question is, when you do extract features out of these pictures or photos, how do you distinguish temporary mobile objects versus permanent objects? Because there could be a sign, but the sign was just putting there to just during the during a short period of time of the construction or repairs, but it's only be there for a few days. I don't know, how do you do that?
Well, one technique is just to have to drive multiple times and to see whether something has changed, and the data that's changing you subtract as not as reliable. So parked cars, for example, are one of those problems. Moving cars that as you drive along, the cars around you cast a shadow for the instrument, so you don't see what's behind them, and so you kind of want to subtract those cars out. They're not really in the map, so you want the ground truth, which is just the street, and I guess there are multiple approaches, just having statistically, multiple runs. So you drive at night, for example, that could be a better way to capture that stuff. And you don't get visual information, so you drive again during the day. Other ways I've seen, but I don't know how adopted it is in the industry, is that you actually recognize, in the point cloud certain objects because you have the ability to do so. So you, for example, say that's a car, and then everything that is part of that recognized car, you just throw away those points because you know that they're not part of the ground truth data set. That has implications on, because you have a feedback loop in the actual learning algorithm at that point. But what do other people do when they know that they have bad data to begin with?
So you're asking, what do you do as you're going through? Now you're out in your testing phase, and you have ways of detecting that there's errors in that. How do you incorporate that? Yeah. So I don't know. The typical thing that I've seen is you can just, the automated way to do this is to continue to add to your training set, and if you collect enough examples of that, then your accuracy improves. But there's this latency because it does take these deep nets. If it's in a difficult image recognition problem with many hundreds or thousands of categories, you're talking about a significant training time usually. And so continuing to add to your, you strive for, sometimes you strive for having a new model out every couple weeks, and that probably won't do it for this kind of application. I don't know.
Why not?
But where you're talking about like a temporary construction zone or something where they have cones up or flashing. So that wouldn't necessarily be in the map. Maybe you could train the network to understand what that means.
It's a novel kind of object that, you have.
Yeah, like the orange signs that says construction from this date to another date, or you have the flashing yellow. I mean, you could train that, but it would be it's not permanent enough to be in the map, but it's something that the sensors can see and then refer to the map that's not there, so it would notice the discrepancy.
But there's a whole spectrum of things that change. Things that change very quickly
Yeah.
are the car in front of you, the bunny that hops across the road, the pedestrians. Things that change a little bit less quickly are the cars that are parked, or maybe the construction sites that change daily or hourly or maybe monthly. And then things that change very little are the buildings and the new interchanges on the freeway. So there's a whole spectrum of how quickly things change. And I think the maps, an important part of these high precision maps that we're talking about is the ability to update from the sensors, to collect information continuously. It's not a typical batch waterfall process. It's almost like the agile process in software engineering. You continuously update, and you continuously do difference detection. Right. And then the aggregation mechanism in the cloud has to figure out whether it's an annotation on top of the base map that says, well, usually it goes straight, but for the moment we have a construction zone here. Or it's just a sensor error or a badly parked car that we don't care about tomorrow.
Yeah, so the map and the sensors will constantly be comparing each other, and any discrepancy will be logged in the vehicle and then updated in a map over time. I mean, ultimately, you have to do it in real time, near real time. There's no easier, but
Well, one aspect is you have to process some of that information in the car because you can't send raw data up. So that the question does become, do I send all the data up or do I send the processing down? I mean, there's a trade-off here. And because we're collecting so much, or we will be collecting so much data, there has to be processing.
What is that data size?
Oh, it's gigabytes. I mean, even today, the cars, there's so many sensors in the cars, some of them you don't care about, but cars today are very autistic. Everything drops on the floor, nothing gets sent home. But when you talk about these future sensors like lidars and radars and ultrasound and video, there's a lot of information. Imagine an MPEG video stream, even highly compressed, that's multiple megabytes a second. And you add, lidar to that, it adds up very quickly. So, but it's not necessary to send everything up.
Right.
But you have to do the difference processing on board.
Some amount of segmentation of objects, of novel objects that you haven't seen. Yeah, it sounds like. Makes sense.
Jason's our mic guy, so.
So we've been talking mostly about HD maps for the computer in the car doing the self-driving, and then, for the cockpit car computer, the thing doing the navigation, your infotainment, stuff like that. There's also a map database with locations, points of interest. At what point do you think that there'll always be two separate databases, two separate sets of maps, or do you think, at what point would they combine and consolidate together?
I think they'll combine together. I think, because right now we do have the traditional GPS map. It's not accurate enough, but as we get the map in the car, I think it'll come together. So you will be using navigation off the HD type map. I think that's where it's headed, but right now that HD map isn't really available. I know, TomTom in here and a few others have map samples out. Most of it is proof of concept, not production grade, not everywhere. So eventually I think I see the GPS type maps going away, and just everything will be highly accurate.
I think maybe I agree with Chris completely. Once you have a car that completely drives itself and you trust it all the time, why do I need a map? I just need to know I'm here, I want to go there, bring me there. I don't care what the street names are in between.
Well, there's also things like, okay, I'm in this intersection and I'm looking for Chinese food, and I happen to know that, I can ask right now, okay, what restaurants are around here? And yeah, or I've seen some demos as well as like, okay, oh, what's that over there? So gesture recognition of pointing, and okay, yeah. So is that going to part of your question as well?
Yeah, I think so. So
Yeah.
it seems like there's general agreement that the databases would merge at some point, and then I guess what Christopher was saying is that probably the database would reside in the self-driving computer, if you will, and then that information gets fed back to the the head unit, the infotainment.
Yeah, I think that's where it's headed. I mean, everything will be there. It's just creating the right way to do it. Because it's not the map you're used to. It looks really messy compared to like a Google map or any street map you're looking at. You got every single lane. You got dividers. You got barriers. You got all kinds of stuff. So to a human, it looks pretty messy, but to the vehicle, it understands. But I think as time goes on, they can customize that look in a HUD display or in a map system to make it more human readable, I guess. Something we're used to, like a video game or something like that.
Mm-hmm. But no one has that. No one has a system like that today in production.
Can't really.
Well, can you talk about NDS? So it's one of the standards that people are pursuing.
So yeah, there's a few standards right now. NDS is one of them, Navigation Data Standard. A lot of the car companies use that traditionally as a a way to update maps. So they don't have to update the entire map. They can update sections. Like if California changes, they can make it just an update of California. But in India, they have an auto drive specific module, which is still under development. So in theory, it's there, but technology isn't really caught up. And that standard isn't something that can be used right now. There's also an open drive standard that can be used to plug map data into a simulator. And Robert knows a lot about how that simulator.
Well, one thing that concerns me, because all the CEOs have promised 2018 self-driving, 2020 self-driving, and if we don't have the maps, is that realistic? Or
I don't think so. Not in terms of. I think we'll see it come in stages. I think some of what we'll look at is like your car can come to you from your driveway or from a parking lot. Let's say I go to the airport. Let's say I'm in LA, leave LA to go to San Francisco. I tell my car that I'm leaving. The car leaves my house and picks me up at the airport. So I think self-driving functions like that might be something, but because then you could focus particularly on certain airport parking lots that allow self-driving. You can target your map that way, but I don't think the map is anywhere close to being. Although there are companies that are able to scale map collection extremely fast and at cost. So.
Well, I'm glad to hear.
Yeah.
Yeah, that's
who knows?
What level of autonomy are we talking in these promises that you referred to?
I think it's level 4, right?
Yeah, self-driving, right? You've heard Elon,
Yeah.
Mercedes.
Yeah.
So it's full,
I mean-
full autonomy.
I think a lot of the sensors are, I mean, your car now has a ton of sensors that, blind spot assist, lane tracking, all kinds of stuff. But it's already on the car. I think what's scary for a lot of the car companies is just letting the sensors do everything. You would never see a traditional car company allow autopilot like Tesla, just because the regulations, the regulations that you have in the auto industry. These car companies can do the same thing, but they're a little bit more safety conscious.
As I said, I'm glad to hear that there's a high demand and not enough supply of this
Yeah.
stuff just yet.
Great discussion, guys. Thank you very much. I had a little bit different question. So we're talking about, sensors, data acquisition, video, LiDAR, and, rapid scene analysis and understanding where the car is relative to various things. What does the panel think about active vehicle-to-vehicle communication technologies that I'm sure you're all familiar with, and what role do you think that'll play in getting us to autonomous cars?
I think, like you said about knowing where the car in front of you is going. I mean, I think the key is, every car talking to each other, each car. I need to know what this car in front of me is doing. I need to know what the car on the side. I think that's kind of where.
Are you referring specifically to technology called DSRC?
Yes.
Okay. So, I'll summarize that quickly. Who doesn't know what DSRC is? Maybe I don't even summarize it. Okay. Very few people. I'll briefly say it. So it's basically a subset of Wi-Fi or something related to Wi-Fi where you generate connections between cars very quickly. So one car can very quickly tell the other cars in its proximity what it's about to do. It's about to go straight or stop or go left or go right. This is a standard that's been evolving for about 20 years. It's mostly been pushed by a board called the ITS. There are several companies that have gear for that now, startups. The National Highway Traffic Safety Administration under Obama has said that they might come out with a ruling that forces car makers to put these things in. As an investor, I'm skeptical because the density required to make that system useful is high. An analog that's always mentioned is if you have a first fax machine, it's not very useful to you because who are you going to send faxes to? You need other fax machines to make that useful. And so if one car around you has that modem, but the other ones don't, it's going to say, stop, 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 and nobody stops because the other people can't, the other cars can't hear it. And there's more to it than that. So I don't want to, if everybody had it, that would be useful, but there are a lot of technical and go-to-market issues with that technology from a startup investment level perspective. I see that every car maker will have to have active sensing from within the car, and the communication is kind of gravy on top of that. But you can't start from the communication because it has too many dependencies from the go-to-market perspective. It's going to be a useful additive to level 3 and 4 driving.
And we have another question from the audience.
So first of all, I think I should address the obvious. Robert, great shirt. That's a really cool shirt. Secondly, I want to just get the panel's opinion about the debate between using LiDARs and cameras. Tesla's approach seems to be camera-centric, where the camera seems to be sufficient to make the car autonomous. But with Robert's investment in Quanergy, you seem to be gravitating more towards LiDARs. So what do you think, what the future is?
Well, cameras have been around for a long time. Cameras are commodity technology at this point. There has been a lot of research done into image processing and video processing. You may know a public company called Mobileye from Israel that has basically put an ASIC behind a chip, a special purpose chip behind the cameras to make processing very fast. That is in fact what Tesla uses currently. There are issues with cameras. Cameras can only see what they can see. There has to be enough light for them to see stuff. So driving at night is an issue. Cameras have a certain dynamic range of lighting. So if the lighting changes very rapidly, there are methods around it, but if the lighting changes very rapidly, like if you go directly into sunlight or you have to go through trees where the light comes on and off, the sensor has a problem adjusting gain control, and that has consequences later. And finally, the subtended angle, the pixels on the horizon, you have the fewest pixels per distance. And that's exactly where you're looking for the most precision. LiDAR is a different technology. It uses infrared light. It's active, so it shines light out, and so it can work in complete darkness. It's also more resistant to these issues about light changing and direct sunlight. Manifests itself as noise, but not complete disaster. The other thing that a LiDAR can do quite well is it can be steered to foveate processing. This is a specific thing that Quanergy is enabling. So you've seen these LiDARs that on the Google car, they're called Velodynes. They're $75,000 and now cheaper. Let's say $10,000 to $75,000. Almost always more expensive than the car that's underneath. Quanergy's difference is that they make a sensor that's a few $100s in quantity, and it can also be steered. So when we talk back to 3D maps, the 3D map can actually say you should expect the traffic light over here. So if it needs to know what the color of the traffic light is, the LiDAR can't tell it that, but the LiDAR can quickly localize and verify that there is a traffic light up there because it can foveate its points, its sampling in that area. And then tell the camera, okay, I see the traffic light up here. Just look at that little rectangle. And so the processing that's required to extract the traffic light color is then much, much less than if you had to process the whole image.
Right. Just a follow-up question. Human beings have been using visual feedback to drive the cars, and we have been doing just fine, in driving the cars. Secondly, Quanergy seems to be the only company, who's trying to bring the cost of the LiDARs down, building solid-state LiDARs. So don't you think maybe the cameras can pull off autonomous driving for a while?
It's not an either-or thing. I think for the car makers, it's a cost thing. And the palette of sensors that they use will evolve over time. I mean, when you make a $15,000 car or a $20,000 car, you cannot put a $75,000 LiDAR on it because you wouldn't sell it, right? So, but a $100 camera, that's doable. And so the sensor packages, the palette of things that people use will change over time. Cameras will remain a component of that because you have to see color. You have to see, verify that that's a white or a red stripe or that's green or a yellow light. But you can use much cheaper cameras if you have already localized the example that I just mentioned.
Okay.
You don't need object detection chippies behind it. You just say, you know, here's a rectangle, what is the main color in that rectangle, and that gives you the color. So the algorithm mix and the sensor mix will change over time, and you will see the newer, higher cost sensors adopted early in the higher cost vehicle.
All right.
All right.
Thanks for coming, guys. Oh yeah, applaud us. Yeah.